Hello and welcome everyone to our poster session. My name is Saeed. I'm a PhD student at Georgia Tech. Today, I'll be talking about a figure of merit for ultrasound transmission in transcranial focused ultrasound. Transcranial focused ultrasound is a promising non-invasive technique for brain diseases. But recent reports show focused ultrasound can cause lesions in the skull bone marrow due to excessive heating. To overcome this problem, shear wave and non-wave mode conversion through oblique incidence has been proposed. Our objective is to investigate ultrasound mode conversion and heating effects in the skull and compare with normal incidence transmission. Using this information, we developed a figure of merit based on the maximum temperature rise in the skull and transcranial transport power to guide ultrasound delivery. We use simulation model K-wave allows us to simulate propagation of compressional and shear waves in viscoelastic media, as well as simulating heating, diffusion, and perfusion in the same media. We assume homogeneous material properties for skull bone. Also, we use perfect plate geometry in numerical model, as shown in the figure right. Parameters are obtained from the literature are used to compare normal and oblique incidence transmission. To obtain power transmission coefficient, we compared spatially integrated intensity levels with and without skull layer, given in the upper right figure. After elastic simulation, the bioheat equation solved with recorded steady-state particle velocity and acoustic and thermal properties. Therefore, we are able to generate temperature map throughout the skull layer, shown in the figure set in the middle. The results show the outer section of the skull bone is heated significantly more than inner section of the bone at oblique incidence angles. Also, the skull layer heating due to shear and compressional waves are separated and added to obtain total maximum temperature rise, given in the figure lower right. It shows the temperature rises follow the similar path above the 18 degrees. The separated temperature rise graph in the left shows the shear wave attenuation is prominent after 20 degrees incident angle, and it dominates after the compressional wave critical angle. With this knowledge, we introduce a figure of merit, which is the ratio of the transmitted acoustic power to maximum temperature rise in the skull. This is shown in the figures in the middle and right. The simulations are performed for a range of attenuation and skull thickness values. The results show normal incidence delivery is more efficient than oblique incidence delivery. In order to validate our simulation model, we carried out a setup experiment. The experiment setup is given in the diagram on the left. The samples are rotated for oblique incidence delivery. The transmitted loss is calculated by normalizing to reference measurements. The example field distributions are in the figure set on the right. We used multiple parietal bone samples have relatively uniform thicknesses. As a transmitter, we used a half-inch diameter unfocused transducer. The results show the best transmission is around the normal incidence angle. Also, the simulation and experiment results share a similar transition drop around the compressional wave critical angle. In this study, we focus on transcranial power transmission and temperature rise as a function of angle for different attenuation values obtained from the literature. Beyond the compressional wave critical angle, a high temperature elevation is observed in skull, mostly due to the shear wave attenuation. The developed figure of merit captures this phenomena to guide transcranial focused ultrasound application. And lastly, below 15 degrees angle should be targeted for the high figure of merit, as followed in the most transcranial focused ultrasound systems. Thank you for your time.